Started.
You got it.
All right, thank you. So hello, everyone. I'm Dr. Kirby Runyon. You can just call me Kirby. And I want to give an update on something that Mark Wagner and I, who is convening this conference, of course, that he and I just got back from. And Brenda was along on it as well. In fact, Brenda has done this with me twice. She did it back to back. Boom, boom. This was at the very end of October. But I want to talk about the planets in your backyard. And really the idea is to understand the landscape of space. I love this picture. This was taken earlier this year on the Unity 25 flight that Virgin Galactic flew with Virgin Galactic employees on board. This was, I think it was in May, and Virgin Galactic launches its spacecraft above New Mexico. And the landscape of New Mexico is what makes up the landscape of space when you're looking out the window. I'll also mention that Blue Origin, which launches private astronauts out of its West Texas launch site, is close enough to New Mexico that you see a lot of the same things. What's so interesting, I think, about the area over New Mexico where Virgin Galactic launches and close to where Blue Origin launches is that these geologic landforms are what we call planetary analogs. They're extremely similar or analogous to similar geologic landforms on planets and moons around our solar system. So these two Virgin Galactic astronauts are looking down at New Mexico, and this black squiggly line you see out the window is what's called the Carrizozo lava flow. It's a 45-mile long lava flow that Brenda and I have been to, and a number of others. So let's move on here. If I can advance slides, come on. Okay, so a little bit about myself. I'm Kirby Runyon. I hold a PhD in planetary geology from Johns Hopkins University. And since 2017, I've been a NASA-funded research scientist using images of planets, moons, and asteroids from around the solar system to understand the surface of these planets and moons. I'm also a zero gravity coach and a zero gravity flight reseller with the company Zero G. Flies this airplane in parabolic arcs to give you not just weightlessness, but it also does the gravity of the moon and Mars. And I'm also an entrepreneur. My company, Planetary Experience, or Planex, is focused on helping people live an outer space lifestyle in various ways. And so that includes space-themed education, entertainment, and public speaking, and other cool events. Okay, so I mentioned Virgin Galactic. This is a picture of spaceship Unity launching itself to space with its hybrid rocket engine. This was actually on Sir Richard Branson's space flight in 2021. And the picture on the right is the view from his spacecraft, looking back at New Mexico. Hopefully you recognize the Carrizozo lava flow, that 45-mile long lava flow. But there's also, here is White Sands, New Mexico, White Sands National Park, White Sands Army Missile Range. There's a lot that's visible from space, and I want people, especially I want space tourists and people who are interested in that sort of thing, to recognize what they see out the window, and also to understand how these geologic features on Earth connect us with the rest of the solar system. Before I get too much into the weeds on this, there's an overarching theme in geology, whether it's geology of Earth or geology of the planets, that is fundamental, and that is that geology, looking at the rocky landscapes and the rock samples, is a forensic science. In a crime scene investigation, a forensic investigator will go to the scene of a crime and they'll look for clues as to what happened. If no one was there at the time of the crime or the incident happened, a detective can piece together little pieces of evidence here and there to recreate past historical events. Well, geologists do the same thing, except that our record is in the rocks. Some natural processes happened in the past to create the landscapes that we see, and it's the job of a geologist to piece those clues together forensically and recreate natural history. And so as we look at these geologic landforms, we can use them as clues to understand how they were emplaced. Okay, I'm gonna zoom back into this slide here. This is our view from spaceship Unity looking down at New Mexico. We've of course got the Carrizozo lava flow, and all of these I'm going to touch on in more detail in the following slides. But we've also got White Sands National Park, the San Andres Mountains. The spacecraft launches out of Spaceport America right here. A place where we haven't yet gone on the ground is the Jornada del Muerto lava flow. Incidentally, the Trinity site where the first nuclear bomb was tested was right up here on the other side of the San Andres Mountains. this here, Brenda, if I'm not mistaken, is the city of El Paso, Texas, and Ciudad Juarez in Mexico.
Yes, yes.
And if we box in over here, we've got two really neat volcanic landforms. We've got Kilbourne Hole and Aden Crater with the Potrillo volcanic field and the Aden volcanic flows throughout here. So I'm going to talk about these more in the following slides. So if we really focus on white sands right now, this is a picture from the International Space Station looking down at the Holloman Air Force Base in Alamogordo, New Mexico. If we zoom in, we can really start seeing the ridged features of the sand dunes. Sand dunes are self-organizing features. If all you have is a sand supply and wind, you'll start getting a set of sand dune features that migrate. And when I was doing my PhD studying these sand dunes on Mars, we actually used white sands quite a bit as a planetary analog. We do have spacecraft orbiting and on Mars, but if you wanted to study these dunes up close, your only option is to study a substitute, these analog sand dunes at white sands. And so since 2006, sometime really, we've had this now fairly old spacecraft called Mars Reconnaissance Orbiter. It's a NASA spacecraft, and it's got basically a spy satellite quality camera on board called the HiRISE camera, which stands for the High Resolution Imaging Science Experiment. And as MRO, Mars Reconnaissance Orbiter, orbits Mars, it just takes very high resolution pictures of the surface of Mars. It's so high resolution that it can see things as small as a pixel on the camera is 8 inches or 25 centimeters on the ground. So this is way higher resolution than anything we've sent to Mars, even since 2006 when it got to Mars. And when we take subsequent images, a picture now and then wait a few months to maybe a few years, and we take another picture of the same area, you can actually see these sand dunes moving in the wind. You can actually see them blowing downhill. You'll note that the general morphology of these dunes, they tend to have this really sharp, smooth area on one end of them. These are called the slip faces. What's happening is that the sand grains blow from, in this case, left to right, and the sand grains accumulate near the crest of the sand dune, and then they start getting sheltered from the wind because of the bulk of the dune, and they just sort of build up on the crest there until eventually that downwind part of the dune over steepens. It exceeds what we call in geology the angle of repose. That's the angle that sediment naturally wants to form when you pour it out. And that slip face will actually avalanche in the downwind direction. It doesn't happen all at once. It happens little bit by little bit, but over time, you can see the whole dune begin to blow downwind. So in a number of years from now, can you guys see my cursor? Brenda, can you see my cursor if I point things out? Yes? Can we see the cursor? Someone can just unmute and tell me yes or no. Do you see my white arrow moving over the dunes?
Yes.
Yes? Okay, great. I started pointing at my screen and then realized I was the only one who could see that, so I'll use the mouse. And so these whole dunes will eventually, all these dunes will have been blown completely from the left off the screen to the east, but that will probably take a few hundred to a few thousand years. You'll notice that a lot of sand gets left behind in craters. Mars obviously has a lot of craters, given its thin atmosphere. There's not a lot protecting the surface of Mars from bombardment. And so the sand can fill in the craters. Oops, I didn't mean to go forward. The sand fills in the craters, and if it sits there long enough, it petrifies, or lithifies, as we call it. And you can see where there were some craters up in here that were filled with sand, and then maybe that sand was covered over for a while, maybe a little bit of moisture or ice got in there and cemented the sand grains together, and it forms sandstone that just fills in the craters there. One of the things that I think is interesting about Mars's dunes, Mars is related to Mars's atmosphere. Mars's atmosphere is the same pressure on Earth if you went up to an altitude of 100,000 feet. Now, on Earth, at 100,000 feet, the sky is black. You can see most of the blue atmosphere beneath you, and you can definitely see the curvature of the Earth. But that's the surface atmospheric pressure for Mars. And so because it's got this very thin atmosphere, in order for it to blow anything at all, it has to be blowing really fast. And so sand grains, even though maybe counterintuitively, even though the sand grains there's not as much wind blowing them as on Earth. Once they are moving, they're moving really fast. And one of the consequences of that is that sand dunes on Mars get to be much larger and much taller than correspondingly similar sand dunes on Earth. Now, in this next slide, this is an animated GIF. I was mentioning you can actually see the slip face advancing downwind. And this is a similar dune, unfortunately black and white, but it's still the same resolution as before. And you can actually see it migrating downwind ever so slightly. So if you see it further up or further towards the north, that's a before image. The image where it's further down is the second image. And we're actually at a resolution now where you can see the individual ripples on top of the dune. So I spent a lot of time in graduate school flipping back and forth between images to measure how far these sand dunes had moved. It was extremely tedious. Yes.
That's a Martian dune, yes?
Yes, that's a sand dune on Mars.
Okay, just make sure.
Yep. Yeah. So it was extremely tedious, and there's a lot of new like AI tools that will measure these things now, but there's also a certain pleasure in just staring all day at the surface of Mars. We've also studied one sand dune up close with the rover. The rover Perseverance. I get Perseverance and Curiosity mixed up. Nope, I got it wrong. This is Curiosity, otherwise known as Mars Science Laboratory, or MSL. I see there's a couple things in chat right now. Okay. Roman, you sent me a direct message. My email is in my name tag on Zoom, so please send me a reminder email if you'd be so kind, and I'd be happy to share some of this with you. So this is the Mars rover Curiosity roved up to the downwind slip face of this dune. This is around 2013, 2014, and we're looking at we're looking upwind at the downwind side of this dune, where sand is coming up towards the camera, accumulating on this crest line right here, and then avalanching downslope. And you can actually see some of these cup-shaped erosional areas at the top here with some of these fan depositions. This is where individual avalanches have served to move the whole dune downwind ever so slightly. This sand dune is named after a guy who's considered to be the father of wind-blown geology science. It's called Aeolian geology, for Aeolus, the Greek god of the wind. And so this dune is called one of the Bagnold dunes in his honor. He was in the British Army during World War II, and he had to do a lot of reconnaissance in very sandy areas in the Sahara. And so that inspired him to actually study the geology of dune movement. And then these aren't dunes, but these are ripples across the surface of Mars. This was taken by a much older rover. This is by the Opportunity rover that landed in January of 2004, almost 20 years ago now. I can't believe it because I watched it land live. These are not dunes, these are ripples, but you can even see the rover tracks where the rover got stuck momentarily. And by momentarily, I mean like a few weeks, and it was eventually able to break out. This was called Purgatory Dune. However, it's not a dune, it's a ripple. Ripples and dunes are different things. There's other places in the solar system with sand dunes. One of them is Saturn's moon, Titan. Titan is one of the most interesting places in the entire solar system. It's the second largest moon in the solar system. It's larger than our own moon, and it's the only moon in the solar system with a significant, thick atmosphere. In fact, its atmosphere, you can't even see the surface of it from space. Like this view right now, this photograph was taken by NASA's Cassini Saturn orbiter. It did a bunch of flybys around Titan from 2004 to the end of mission in 2017 for those 13 years, and took a lot of data of Titan. Titan just looks like an orange puffball with blue haze around it. And you need radar and infrared to see through the haze, the cloudy haze, to the surface of Titan. But the surface of Titan actually contains basically the entire equator of this moon is covered with a sand sea. I mean, it's just sand dunes just wrapping around the entire equator. Incidentally, the south pole of Titan is covered in lakes, but not lakes of water. They're lakes of liquid methane. And so the sand on Titan, we're pretty sure it is the result of grains of ice, just frozen water, getting coated with sort of this organic soot that is the result of methane in the atmosphere. I like to call it getting sunburned. Ultraviolet light from the sun is causing the methane molecules to break apart and then reconnect into these really big molecules that end up forming this soot, this carbon hydrogen rich soot. And it eventually not quite snows, but it falls out of the sky. There's nothing quite analogous on Earth. And it coats these sand grains, we're pretty sure, and then the sand grains get blown by the wind and cause these dunes. So we have a mission going to Titan. It's launching at the end of the 2020s, getting there in 2034 or 2035. It's NASA's Dragonfly mission, which is fantastically exciting. It's literally an octocopter drone that's going to fly around the surface of Titan, and it's going to study some of the sand dunes up close, but you got to wait till the mid-2030s to see that.
Hey, Kirby.
Yes.
There was a question before you go to the next slide, asking what would be the average temperatures?
Yeah, great
here.
question. For Titan, it's 96 Kelvin. That is 96 degrees Celsius above absolute zero. Someone could do the conversion to Celsius or Fahrenheit. To put that into perspective, though, that's much colder than dry ice, but it's warmer than liquid nitrogen. So if you go to the dermatologist, you get a wart frozen off, that liquid nitrogen is 77 Kelvin. Liquid hydrogen that's used in some rockets is even colder than that. That's around 20 or 22 Kelvin. So we're still talking cryogenic temperatures. We're just a little bit above the liquefying temperature for oxygen, which I think is in the 80s of Kelvin. So it's cryogenic, it's quite cold. It's just above the liquefaction temperature for nitrogen, which is still mostly the atmospheric composition. Titan's atmosphere is something like 96% nitrogen and 4% methane, but that 4% methane is enough to color it like an orange ball.
Gotcha, thanks.
Yeah, here's a radar image from Cassini of the sand dunes on Titan, and you can see it's almost as if like God or somebody had taken a comb to a giant's hair and just sort of like combed the hair, and you can see these are massive sand dunes. These are huge, kind of flowing around. These are probably mountains or hills or some sort of topographic obstacle, and so there's a fair bit of sand dune movement flowing around these. And of course, you can't go to Mars or Titan, but you can go to White Sands National Park. This is a picture of a bunch of us pointing to of our shadows pointing to space at White Sands. When Brenda and I were there, and Mark and I were there for that matter, just at the end of October, just a couple weeks ago. And we went to a place very similar to this and hiked out over the sand dunes and saw just gorgeous, breathtaking sunsets. So this is from a trip I took last year with Virgin Galactic astronauts. This is getting close to sunset. It's just incredibly beautiful. It's $25 a car to go visit, so go there. This is you can visit the planets in your backyard when you go to White Sands. You can lead an outer space lifestyle when you go to White Sands National Park and just take in the beautiful sand dunes. That's me looking like I'm about to sneeze, although not actually sneezing, talking to our group of mostly teachers, STEM educators, about the geology of White Sands and how it relates to space. There's a person out there. This is getting close to sunset. We timed our arrival here to coincide with sunset, and it's just stupefyingly beautiful. Okay, moving on from White Sands, I think we're going to the Carrizozo lava flow next in this presentation. Carrizozo is not that far from White Sands, although the southern part of it, which is to the left here, is controlled by the Army missile range. So you can't go there as a civilian. And we did go up here to the northern end, which I'll advance my slides to. And in fact, there's a U.S. road that cuts across part of the lava flow, and there's a visitor center actually right here. It's the Valley of Fires recreation area, and they've got campsite hookups and primitive toilets out there. One of the things that's so cool about Carrizozo is it's a place in our earthly backyard that's similar to certain places on the moon. And one of those places is this former lava river called Hadley Rill. And we actually sent astronauts there in the summer of 1971. Brenda, was there a question?
No, sir.
Okay. So this is a place called Hadley Rill on the moon. This was formed from a lava river coursing through there. It might be a collapsed lava tube, although I'm skeptical. I think this might have been open channel flow. And this is astronaut Dave Scott with his lunar rover looking over the rim of Hadley Rill in August of 1971. Let's see. This is another location on the moon where we see lava rivers ending up in a lava ocean, basically. Right here, this channel right here, this is the largest former lava river on the moon. This is simply called the Cobra Head. And if you really zoom in, you can see there's almost like a lava river within a lava river here. This would have been like a Hawaiian style fountaining volcanic eruption right over here. This would have then flowed north, arcing back around to the south, and filled up this big smooth area right here. This is Oceanus Procellarum, or the ocean of storms on the moon. So probably most of us will not go to the moon, but maybe some of us will. Moon is close enough. But you can at least visit aspects of this by going to the Carrizozo lava flow in New Mexico on Earth. Next slide. Okay, so if we get into the Valley of Fires recreation area here, this is just a screenshot from Google Maps. You can see all of this is just lava. This is the same overall type of lava that's in place on the moon. Those dark areas on the moon that you look up to at night, those are all cooled lava flows. Let me just go back here. I think a lot of people don't realize that all the dark gray areas, in contrast to the white areas, those are all cooled lava flows, massive lava floods even. So this is all lava flow in place from lava rivers like this. And this is Carrizozo on Earth, and it's pretty similar. From the ground, you can sometimes see the openings of lava tubes when you're on the ground there. This is similar to a lot of places on Mars. This is, I think, in Gusev Crater, which is where the Spirit rover explored from 2004 to, I think, about 2009, when its solar panels got coated with dust and it stopped producing enough electricity to function. But the whole floor of Gusev Crater on Mars is also coated in lava. Well, you're probably not going to Mars, but you can go to the Carrizozo lava flow and see those lava flows up close. This is a really fun picture. There are these massive areas where the lava flow, I kid you not, it literally inflated. This is something lava flows have a tendency to do. They get this skin, this cooled rocky skin on top of them, but then the liquid lava underneath is still kind of coursing through, and it puffs up the lava flow, and then of course it cracks, and it's like the top of a cracked muffin or loaf of bread when you've baked it, and you can climb up into it. This is me explaining to our group of teachers, this is just 2 weeks ago, about the Carrizozo lava flow and how it relates to similar places on the moon and Mars, and also Jupiter's moon Titan. These are just some fun views of our time exploring these lava inflation pits. I mentioned that these lava flows can it can inflate, but sometimes they'll hit this topographic high, and then the lava flow will inflate around this like donut hole, and then it just sort of inflates around there, and you end up with this pit. It's not that anything dug the pit out, it's that the walls around the pit grew up. Let's see. Here's just more pictures of the same thing, kind of exploring these rocks. On this sample, we're looking at this really drippy texture, they're basically lava stalactites that formed on the roof of a lava tube, and it was like lava dripping down, and it still preserves that very drippy morphology on this rock here. So that was fun. Another place on Mars that we like to experiment with or try to visit are the Tharsis volcanoes. There's four big Tharsis volcanoes. There's the most famous one. There's Olympus Mons. It's the largest volcano in the solar system. It's got a footprint about the size of Arizona. But there's three other large volcanoes. They're smaller, but they're still huge. There's Ascarius Mons, Pavonis Mons, and Arcia Mons. And this is, if you'll forgive me, this is one of those three. I think it's Ascarius Mons. And you'll notice these series of craters at the very summit of this volcano. These are not impact craters. These are volcanic craters. We also use the term caldera when we're talking about volcanic craters. And one of the places we go to on Earth is similar to this. So this is another aspect of how we can have the summit of Ascarius Mons in our backyard. This is a sort of simulated view from Google Mars, which if you just get into Google Earth, there's a little button at the top. It looks like a cartoon planet. You can switch to Mars on there, and you can kind of explore what it would look like standing on the crater rim of one of the Tharsis volcanoes. And so that takes us to Aden Crater. Actually, Brenda and I tried to go here, but then we got rained and hailed out. Like we just parked, we were walking up to this about a half-mile hike, and then the storm just unleashed on us. So we weren't able to see it, but I've been there on a previous trip. And this caldera, this volcanic crater, is very similar to these other craters on Mars, these other volcanic craters on Mars, but it's much smaller. This is only like 1,700 feet across as opposed to like dozens of miles. This is a place that's visible from space. This is a Virgin Galactic a future astronaut friend of mine, Ken Bowden. He's also a geologist. This is standing on the uplifted rim of Aden Crater, this volcanic crater, and we're looking out into the vast Potrillo volcanic field, just lava flows, just for as far as the eyes can see almost. You can, if when you're standing there, you can see these areas where lava rivers came up out of this crater and flowed down slope around there. This place is such a fun place to just explore around. You can see different crater you can see different flow morphologies in different aspects of the crater wall. This is actually a crater within a crater. So this is another volcanic crater inside the bigger volcanic crater. Again, probably none of us here are going to go to Mars, but you can go to Aden Crater and you can explore the planets in your backyard. Another volcanic crater that's not too far from Aden Crater, and this is a place where Brenda, Mark, and I have all gone just recently, is called Kilbourne Hole. And it's a different type of volcanic crater. It's called a Mar crater. That's spelled M-A-A-R. And multiple ones are Mars, not to be confused with the planet Mars. And this formed 47,000 years ago, but it formed in a completely different way. This is what happens when you mix magma and an underground aquifer of water. And that magma comes up into that water aquifer and it flashes it to steam violently and blows these holes in the ground. This formed 47,000 years ago over a time span of, we think, 1 to 10 years in a series of large explosions that formed this very irregular, jagged explosion crater. Now, because Mars has a lot of lava, a lot of magma, and Mars also has a lot of ground ice and therefore groundwater, and ice is easy to melt if you're a blob of magma, you would think that these types of Mar craters would be all over the place on Mars, but they're not. One of the big outstanding mysteries is why there are no Mars on Mars. So this should be a planetary analog, but it's not exactly, simply because we haven't seen Mar craters on any planet off of Earth. So it's still a really interesting place. NASA astronauts actually train here just because of the steep topography. There's lots of really interesting geology around here to explore. In fact, the rock that Brenda held up to the camera just before we started this, it's got those green these green grains of the mineral olivine in there. And those were brought up to the surface from really deep underground. And we can't even drill that deep. So the only way we know that those kinds of rocks exist is because Earth was kind enough to volcanically erupt them for us. And it formed, the gem variety is peridot, which is the August birthstone. But you can see these in certain places along the rim here. I was on a cross-country flight leaving Tucson en route for the East Coast and just happened to fly by. And so I saw it out the window. And I had been studying it, seeing it in Google Earth before, but I've never actually seen it. This is before I went there on the ground. And I got really excited. I took a bunch of pictures of it as our airplane flew by. And actually, Aden Crater is right over here. So Aden Crater is also in this view from just a commercial. I think this is a Southwest Airlines flight. Here we are on the rim of Kilbourne Hole just a couple weeks ago with our group of teachers explaining what's going on. A lot of the rock in the area is it's jointed. It's cracked up in an almost hexagonal pattern. It's a type of rock called columnar basalt, and it's just a consequence of how sometimes lava cools. In order to minimize the stress inside the rock, cracks will form at angles of about 120 degrees. And if you've got all these cracks forming at 120 degrees to each other, you end up with this hexagonal pattern. And you can see that in the wall rock around Kilbourne Hole. Here's down inside the crater. Here's Mark. Here's a lot of our teachers. But one of the cool things is that you see kind of normal lava flows. That's this sort of like rusted unit here, extending over here. And then right above it is where you get all these piling of volcanic ash that resulted when the magma hit the steam and exploded into a cloud of volcanic ash. And volcanic ash is just very tiny. In the words of Monty Python, very small rocks. And then it's not wind blown, but it is blown by the, it's kind of a wind, the blast of the atmospheric gases escaping. So when you look at the side of this, it looks like it's been wind blown, and it hasn't been wind blown by the regular wind, but it has been wind blown by a volcanic wind. And this is a really cool spot inside the crater where you can really see these nice, sharp geologic contacts. And so this is the type of rock that Brenda was holding up to the camera at the beginning of this session. This is the mineral olivine, this beautiful green color here. And the type of rock that it's in is a mantle xenolith. Xenolith, if you break it apart, xeno and lith literally means alien rock. But it's not a rock from space. It's not that kind of alien. It's an alien from deep in Earth's mantle that was brought up by these volcanic eruptions. Okay, so if I've piqued your curiosity, our last trip was, we were hoping to run these trips a few times a year. This last time we charged $6.99 for the tour fee, and we stayed in Holiday Inn Express in El Paso. We're hoping to do this again in March and maybe again next October. So if I've piqued your curiosity, we do run these trips for educators. And I think that QR code will take you to this website. That's what I have in terms of prepared slides, but I'd be happy to go back and answer questions, talk about other things, look back at past slides, etc.
Thanks, Kirby. That was awesome and such great memories. There is a question in the chat on how on Mars, how can we differentiate the lava flow from the river beds?
Oh, great question. Okay, so let me let's see. Yeah. So we often have to use a technique called spectroscopy. That's where we take the light that's been reflected and we basically have to put it through a fancy prism, break it up into a rainbow of colors. And every substance in the universe has sort of a unique rainbow. And this is a rainbow that extends into the ultraviolet and into the infrared, where it's brighter at certain colors or wavelengths and it's dimmer at certain colors or wavelengths. And so we can tell what the sediments are or what the rocks are based on the spectrum. So if there was water flowing over like sandy volcanic rock, sandy basalt, that water would chemically react with the minerals and actually start forming clay minerals. And so and that shows up in your spectrum. Another way you can look is sort of the morphology. River channels on Mars that were formed from water tend to be a little bit more spidery. They're more twisty and bendy, and flows formed from lava tend to be a little straighter, but that's not a slam dunk. That's not a surefire way to differentiate it. There's an outflow channel called Athabasca Vallis on Mars, and for the longest time we thought it was formed from flowing water coming up from underground, but as time goes on we're pretty sure actually it was just formed from flowing lava. Oh my gosh, sorry, someone just came in my room and scared me. Okay. I'm gonna chill out here. Okay, we're talking about lava on Mars. That's how we differentiate it. Does that answer your question, Harshil? I'm sorry you guys had to see that. I'm easily startled. Someone asked, Nick asked if the sand dunes reminds him of what Matthew Lepotre has done. Has my work been influenced by him? Yes, and I know him. We were graduate students at the same time, and he has done a lot with the physics of windblown sand and also water mobilized sand. And yeah, he's a professor now. I'm not sure where, someone might know. Yeah, he's sort of really kind of dug in deep and kind of focused on this mechanism to be sort of an expert in. But he's done a lot of work on understanding windblown ripples on Mars. A curious thing about Mars is even though its atmosphere is so thin, the viscosity of the air, which we don't normally think of how viscous air is. We tend to think of ketchup as being high viscosity and water as being low viscosity, and that's true. But any fluid, including air and gases, has viscosity. And Mars's atmospheric viscosity we think is actually higher than Earth's atmospheric viscosity, and that could influence the shape and size of the ripples. Okay, so Matthew is at Stanford. Thank you, Nick.
Fascinating. In the absence of other questions right now that I'm sure people are percolating, one of my questions that's been inspired by both listening to you, reading about your work, and now having been able to participate, and I understand the uniqueness of what we got to see here in the New Mexico, so there's New Mexico region with respects to the Virgin Galactic flights in particular. But as commercial space opportunities expand going forward globally, can you imagine other places, or what other places around the world might these kinds of experiences that you offer as far as a teaching thing,
yeah,
also be an option, and to what extent can we start tying in like cultural connections to all of that?
Oh, I like that. Yeah. Virgin Galactic, they're a few years away from this, but they have talked about expanding operations, not just in Spaceport America in New Mexico, but other places. I think the Middle East, especially in around Dubai in the United Arab Emirates, is a future hub of the space experience economy or space tourism. And so I can easily imagine space flights taking off from around Dubai and flying over the Gulf region, looking at the Arabian Peninsula. Um, Ironically, some of the best geology in the region is in Iran. Unfortunately, there's some geopolitical challenges with studying the geology there. But there's all kinds of fascinating geology in the Middle East. The Negev Desert of southern Israel has a lot going on. Other places where this could happen, I could see this happening in Florida. Already, the company Space Perspectives is looking to fly customers not quite to space, but to the edge of space in high altitude balloons that get up to 100,000 feet. And so they're going to be seeing the coastline of Florida. They'll see Lake Okeechobee, and the wind will carry them south to see the Bahamas, which I understand from astronauts' reports are one of the most colorful, eye-popping things you can see from space. Just that turquoise blue water, which is formed, and there's a great geological explanation for it. It's formed from lots of carbonate, so like baking soda in the water that forms naturally. Small microorganisms called foraminifera make their shells. They're microscopic organisms that live in the oceans. I'm not like an expert in them, but I know about them. And they create exoskeleton shells by taking calcium out of the seawater and reacting that with carbon dioxide in the atmosphere, or sorry, in the water, dissolved in the water, because there's carbon dioxide dissolved in the water, just like there is in the air. And forming calcium carbonate, which has the chemical formula Ca, calcium, CO3, not CO2. There's an extra oxygen on there that's CO3. And that forms that white shell. And then when they die, they settle down to the bottom and they get compacted and they form limestone. If they get really deeply buried and heated, that can be metamorphosed into the metamorphic rock marble. And so you're seeing that process happen over the Bahamas. And so future flyers of Space Perspectives will be watching carbonate sedimentology happening in real time. And so any Virgin Galactic flights happening in the far future out of Florida, if you'll be able to see the Bahamas, you'll be able to see that sort of carbonate sedimentology as well. I think the UK is fairly keen on bringing more space operations there. I could see Virgin Galactic operating there, or another space company operating out of there. There's not a lot of great planetary analogs in the UK, but I mean, you'd see the British Isles from space. It'd be cool. You'd see wine country in France, so obviously you'd have to go check that out. So hopefully we'll see more of this expand in other places of the world. I've been hearing rumblings about a Chinese company offering tourist rides similar to Blue Origin. There's some fantastic geology in western central China in the Taklamakan Desert. I've not been there, but you can explore it in Google Earth, and it's just gorgeous. I doubt they'd be flying anywhere near there, but that would be cool. I see a question from AC. Would lava tubes on Mars and the Moon and the Earth differ from each other due to lava composition, gravity, etc.? Good question, and the answer is probably to yes. Earth's lava is enriched in sodium. We don't think of sodium as a huge constituent of these rocks, but it is. And Earth also, and the Moon has a lot more iron in its volcanic rocks than Earth does. And so the lava can be much less viscous and runnier, basically, on the Moon. Probably something similar on Mars. I'm not as familiar with the composition. Let me put it this way. I am more familiar with rock compositions on the Moon than I am with rock compositions on Mars. But the differences in gravity could be definitely important. When Mars has 38% the gravity of Earth. The Moon has 17% the gravity of Earth, or also 1/6 the gravity. And when you turn down gravity, other forces like viscosity or surface tension can become more important. I've been on a parabolic flight that recreates moon gravity, 17% the gravity of Earth. And when I tried to pour water out of a bottle, I had to shake it like ketchup. And then I just got these blobs of water coming out because the surface tension was just as strong as the weight, the force of the gravity on the water droplets. And so yes, lava, or the composition, how much silica, how much iron, how much sodium, and the gravity levels, whether it's 1G, 38% G, or 17% G, can affect the lava flows. Yes. Okay, so Nick asks another question. In the picture of white sands from the air, the bright white sharply contrasts with all the surrounding area. What is a geological explanation for this unconformity? There's a great geology word there, unconformity. Yeah, so that area is it's a lake basin. Back in the day, back around the time of the last ice age, 7 to 12,000 years ago or so, there was a lake there that's been sort of posthumously named Lake Otero. And that was, I mean, so basically it's a basin. It's topographic. The short answer to your question, Nick, is that it's a basin. It's this topographic low. Water collects there. Minerals from the rock that are rich in the mineral gypsum dissolves out into the water. When the water evaporates, it leaves the gypsum crystals called selenite behind, and then the wind can come along and tumble it apart, break it up into sand, and form the dunes. So I think, and also White Sands is bounded on the left by the San Andres Mountains. So you've got a mountain range within a lake basin right there, and I think most of that can explain why there's a fairly sharp contact between white sands versus not white sands.
Cool. Every time I hear you talk about the area, I always learn something new. And it was really fun listening to all of the questions and seeing the enthusiasm of the teachers that participated.
Yeah.
What I didn't get to ask, and what your experience is with respects to a growing curriculum around planetary geology at the K through 12 level, and how what you're doing, creates resources, and your plan or what currently is there that might help with the people that are here today. What is it that's growing, and how do we? I don't know the answer to this. That's why I'm asking, selfishly, so I can create, pathways to help our teachers here in El Paso. But I don't know how. It's a very general comment question.
Yeah, I'll have to think about that. I'm not sure quite how to answer that, except that anything inspired from this, anything that gets kids outside, gets them away from a computer screen or an iPad screen, gets them away from a Scantron test, and gets them outside looking at the rocks and reading the forensic clues in the rocks, even if it's really simple, even if the teacher like planted it in like the parking lot, like even that would be a type of analog activity, a planetary analog activity that I think could excite kids, make it memorable, make them curious. A curious student is going to teach themselves. That's the kind of student you want, is a student who's naturally curious. I would say more so than one that's motivated by grades. And so, I'm not a K-12 educator. I want to help and be a resource. When we took teachers out into the field, I think the earliest grade we had representative was like 7th grade. And, you could see the wheels turning. They were getting ideas for classroom activities for their students, at least for middle school. And I would imagine similarly for elementary school. So to kind of obliquely come in at your question, Brenda, I think the opportunities are to train teachers, to get teachers outside, away from a computer screen, away from an iPad, out looking at the rocks, looking at the forensic clues. And then what Mark was doing while we were there, asking these leading questions about what kind of classroom activities could you do? How does this translate to your school for your unique circumstances? If you're an urban school and there's not a lot of places to go outside, is there something you could do in the parking lot even even if it involves planting fake rocks out there and then having like this Mars rover traverse or something? Or if you are in an area that has access to the outdoors, just going around outside, looking at rocks. It's more interesting than some people think.
Cool. I love it. I don't think there's looking for other questions from the group here. QR code backup, please. Yes.
Now, is that the QR code, Megan, for, I'll put the link in the chat also. I think you're talking about for the Aries Learning, for the
Yes,
astrogeology
yes.
registration site. So, yeah, okay. So this is for the trip we just ran. We haven't updated it yet for future trips yet. Mark and I are still figuring that out.
I
But
was just looking at our messages though, Kirby. I think we settled on March 22nd to 24. So you guys
does
are
that
interested in going.
I know, but does that correspond? We got to figure out if that corresponds with spring break.
Spring break varies widely, so there's no point.
Okay, all right.
As long as we avoid Easter, is the best we can do.
Okay. Yeah, so there it is. Hopefully, I mean, I could share screen again and get the QR code up. But that's the link.
But yeah, it's arieslearning.com/astrogeology.
I'm sorry, what, Mark?
Oh, I was just saying it out loud.
Oh, okay.
So,
But yeah, it was a blast. I popped into you talking about it just now. We would get to a location and Kirby would get everybody out of the van and we'd look at the rocks and look at the landforms and Kirby would share all kinds of information and show us and share with us. And then we get back in the van to drive to the next location and it was time to discuss space education. And it took all the material from my book and my course and just turned it into discussion questions for the van. It was a good context for it. And the discussion was rich.
it was very rich.
Yeah.
Rich. Like a question. Go ahead.
One second. I'm gonna add a sign up, just like an indication of interest form. An indication of interest form in the chat. So if you'd like to be considered for a future trip, we can add you to our email list and advertise it once we've kind of got that information up. So I am putting that in the chat momentarily.
What happened to the
there? And so that link will take you to a sign up form where you can just indicate your interest. You're not committing to anything. There's no money involved. It's just saying, hey, I'd be interested in doing a trip like this in the future.
someone posted?
And then tell your friends.
I saw a question momentarily in the chat and then it disappeared on my end. So if there was still a question, please feel free to ask the question or repost it into the meeting chat. But in the meantime, a question for Mark and Kirby from a host perspective. The fact that, you know, as educators, you know, we build these curriculums, we build these experiences, and, you know, the length of time from the original idea to the actual implementation of the thing. For each of you, what was the aha that was a result of this now experience and seeing this work finally come into reality that inspires you to keep doing this and working with the educators?
This is one of the few things that doesn't feel like work to me. It's fun. I've been wanting to do this for over a decade, something like this, and it took Virgin Galactic starting to fly and Blue Origin starting to fly for things to really come into fruition. I ran a trip for Virgin Galactic almost 2 years ago. I've been dying to get outside. I'm a planetary geologist, but most of my work is in front of a computer. And I'm just desperate to get outside and look at rocks myself, and might as well bring people along with me while I'm at it. Kind of diversify my own funding portfolio so it's not just NASA grants. So, I mean, and then, you know, Mark and I met through you know, kind of a space community and talking about what we both do. And it seemed to make sense to kind of merge our two worlds here, geology and education, and space science too, space and earth science combined, because it's planetary geology. And it just kind of made sense. And so like last spring, we kind of tossed around this idea and kind of set it for October, and it felt like it never was going to come. And eventually, of course, it did. And I think it went better than we really expected.
Mark, was there a takeaway for you from you that inspired you that wants, you know, to keep making this happen for others? If he's still here. And he may not still be here. So in the meantime, there's a couple of questions back in the chat.
Oh, I just tersely answered one of them, not to be impolite, but is there a layer of solid or liquid after layers of gas in a gas giant? Yes, / we think so. As you go down in Jupiter, Saturn, Uranus, or Neptune, the gas gets thicker and thicker and thicker until it kind of becomes this soupy, liquidy, high pressure liquid, and then it probably becomes solid after that, but there's no surface. There isn't a spot where you can say, here's the solid surface, and above it is not solid. It just gets thicker and thicker. It's like runny jello and then really thick, firm jello, as a food analogy. And then what is the best example of a caldera, such as the Valles caldera in New Mexico, that can be found on the moon or Mars? So is this person, AC, are you asking about caldera for Earth or a caldera for the moon or Mars? Because there's some fantastic calderas on Mars, the summits of the Tharsis volcanoes. There are a lot of calderas on the moon, but they typically are not at the top of very prominent mountains, but there's still a lot of volcanic vents on the moon. But there's a lot of calderas in New Mexico, Arizona, and Southern California, and a lot of the volcanic fields around there. So hopefully the answer was somewhere in that.
Any other questions from folks? So you can just pass through them in hypothetical situations, I guess is the next question.
I think this is referring to gas giants. The answer is no, you couldn't just pass through a giant planet because it gets super high pressure, it would crush you, and then it would be like a physical barrier that you couldn't really get through. But it just goes from gassy to solid, but there's no like distinct transition as you go through, or so we think.
Okay. We are at 20 minutes after the hour. We're scheduled to end at 30 minutes after the hour. Is there any last words that you want to offer, wishes, visions, wisdom, questions that you want us to consider now, having been part of listening to your experience and vision?
Yeah, sure. Thank you. I guess wherever you're living in the world, figure out what the rocks are around you, or if you don't like your rocks, figure out some place where you can travel to and go explore those rocks. See what they tell you about Earth history, and then do some research and figure out what it can tell you or how it's similar to geology and other places of the solar system. This is a way that you can, on the education front, you can get both Earth and space science types of education. The universe doesn't know that we've split science up.
Oh no. We lost him. Oh, he froze, unfortunately.
One of my favorite resources for looking at geology on the moon is from Arizona State University, and it's this very easy to use mapping software. It just runs in a web browser. It's called QuickMap, quickmap.lroc.asu.edu, and I just put it in the chat.
Oh, good, thank you. Yeah, you froze there for a moment, so we're hoping we didn't miss too much of what you were saying.
Probably not.
But that's good. I've always loved picking rocks. I have a whole series of different rocks sitting on my desk. I have this one that I found that reminds me of a moon crater. You can't really see it, but I keep it there with my little astronaut guy as a pretending like I'm on the moon. And
oh, nice.
So I love the great suggestion. Can you suggest some places in West India?
Not off the top of my head, but if you get onto Google Maps or Bing Maps or Apple Maps, turn on the satellite view, look for some landforms that look weird and that look interesting. You can find some places yourself in India. I know northern India, that's where the Indian subcontinent has crashed into the Asian continent and formed the Himalaya Mountains. And probably some of India's crust has gotten pushed down into the Earth's mantle and possibly started pooling close to the core mantle boundary. So there's definitely some amazing geology in India. I'm just not familiar with West India, but that's some research you can do just by looking at, mapping websites that are available to all of us. Wow. Okay. Big. Oh, thank you for that direct message. I may, could you email that to me, please? That's long.
Okay. And then there was a question about the Deccan traps in India. Is that
Deccan traps?
Did I say that right?
Yeah, Deccan traps is I don't know a ton about it. It's what's called a lip, a large igneous province, and massive volcanic eruptions forming these seas of lava. Those sorts of eruptions don't happen on Earth these days, and it's a good thing they don't, because they would be at least nation ending. And just the amount of climate change, that like instantaneous climate change from these massive volcanic outpourings would trounce our ability to adapt. And so the Deccan traps are one such example of that.
Well, we're basically almost at the end of this particular session. Unless there's something else that we want to make sure we have recorded for posterity, I'll go ahead and stop the recording at this point. Kirby, is there anything else?
I think that's all from me.
Okay, let me stop the recording.